Let's start with the obvious. Ancient shorelines, strand lines, benches on the hillsides created by wind blowing across the surface of the old lake. Tells us the water was 1,000 feet deep here. But there's not just one old shoreline, there are dozens of them. Different lake levels. For the Montana valleys that had Glacial Lake Missoula in them, the old shorelines are best seen on northwest-facing slopes, like the hillside above the University of Montana. The Big M above campus, 620 feet above the town of Missoula. This is only 2/3 of the way to the top, the high water mark. The highest strand line is more than 300 feet above us. Hiking up this slope, you might expect real obvious notches, benches, cuts dug into this slope, but they're subtle. These old shorelines are more obvious from a distance than hiking right on top of them. T.C. Chamberlain was the first geologist to note these faint watermarks in 1886. He had read reports describing Scotland's parallel roads of Glen Roy and correctly interpreted the elevated shorelines here in Montana. Each glacial Lake Missoula strand line was created by lake waves eroding into the hillsides. But shorelines are also places of deposition. Beach gravels have been found. Little beach berms. So far, no preserved organic carbon or other datable materials have been found at the old shorelines. So telling a decent story here is difficult. Missoula, the Big M above campus, the strand lines on the hillside. Even though we don't have specific dates, most geologists agree that the highest strand line is the oldest lake. That the strand lines get younger as you go down the hill. The thinking is, if there was a young lake up here, and then you drain the lake, wouldn't you wipe out all these older strand lines? That's the thinking. Older, highest, younger, lowest. Yes, that's the thinking, but without datable material, even the most basic questions remain. Is each level a different glacial Lake Missoula? Or is this one lake with periodic lowering, or a combination of the two somehow? Without dates for each shoreline, it's still unclear. The highest strand line is at 4,200 feet elevation. On a steep hill slope, exposed to more than 10,000 years of thunderstorms, it's pretty amazing how little eroded these strand lines are. At its maximum, Glacial Lake Missoula had a surface area of 3,000 square miles. The northern shorelines of the lake sometimes had an ice margin. Ice calved off into the lake, icebergs with big rocks in them that set sail for various destinations in the lake. Large boulders show where the big rocks fell off their ice rafts. Drop stones, back when the water of Glacial Lake Missoula was relatively calm and quiet. Up north, impressive white lake beds were laid down close to the ice margin. Rock flour, silts created from the grinding power of the ice sheet to the north. Wildlife and dusty white deposits everywhere. The drain was plugged, the lake was big, and the white silts collected on the quiet lake floor. But there are also deposits that speak of tremendous high-energy events. Mud is usually at the bottom of lakes, right? You swim in your favorite lake, that means dark mud is oozing up between your toes. But at the bottom of much of Glacial Lake Missoula, deposits of rocks, not mud, dominates on the valley floors below the strand lines. Why? I'll bet you know why, right? High energy water is recorded in these valley bottoms. That's what the rocks are telling us. But when Glacial Lake Missoula was here, it wasn't high energy, it was low energy. The water's just sitting there, and layers of mud and silt are being deposited at the bottom. But when we break the ice dam, that water starts moving quickly, fast enough to erode all those soft beds at the bottom And in their place, a big batch of river gravels were brought in from elsewhere and sit at the bottom, deposited during the high velocity flooding. Rocks the size of my fist or my head or even bigger. So when we look down the guts of the Clark Fork River Valley, it's high energy river gravels in the bottom instead of the mud. Okay, make another ice dam, make another lake, lay down more silts and muds. That's fine. But when we break that ice dam, the water's on the move and we erase those and bring in more river gravels. All told, we have more than 300 feet of big flood deposited gravels at the bottom of the Clark Fork River Valley. How many floods does this represent?